So, welcome back student to our complex analysis course, where we are in the process of learning line integration. In the last class we show some real function and how to do the line integration. So, line integration. So, today we will start with function z square. This is the function that is given. So, this is some sort of example I am doing. Here I need to evaluate this particular function z square for three different paths. So, the problem is there are three different paths is given. So, one is one path is I need to go this point 1 1. One path is from 0 to 0 I need to go. One path is this. Second path, this is 0 to 0, this is 1 1. Second path is this to this. And third path is this. So, there are three different paths that is given to you, that I am going from this point to this point and this point to this point. This is one line or path. This point to this point and this point to this point another path, and directly from this to this. So, I need to go 0 0 to 1 1, 0 0 to 1 1 and 0 0 to 1 1. Both the cases I am going to the same point to same point, but the approach is different. So, let us do the calculation. This is path 1, this is 2 and this is 3. So, z is x plus I y and z square is x square minus y square plus 2 I x y. This is the two thing I have. So, now for path 1, so the function f z dz is simply be see this quantity x square minus y square plus 2 I x y multiplied by delta z, which is dx plus I dy. This is the complete form of the integration. I need to evaluate these things for these three paths 1, 2 and 3. This is path 1. So, now let us start with path 1. So, path 1, if I calculate here, so let me erase this part and calculate here. So, the integration 1 means I am doing the path 1. So, x square minus y square plus 2 x y, here I am going to from this path to this portion to this portion. So, when I am going to this portion to this portion, there is no change in x. So, let me define x, y and here this is x, this is y, this is y, this is x, this is x, this is y. So, I am going from here to here. So, there is no change in x. So, only change in y. So, x is dx is 0 and also x is 0, because this point x is fixed and the fixed value is 0. So, the first part, so f z dz simply comes out to be this quantity what I put, this is 0, this is minus y square changing, x is 0 along this path, so this quantity should not be there, dx is also 0 because there is no change. So, only thing I have is I dy. The limit from here to here is 0 to 1. Next I will go from here to here. So, I just divide this entire path C into two parts, C1 and C2, that is all. So, entire path C, if I call this is the path C, then I divide this into two parts. The next part, what happened? In the next part, my y is fixed and this fixed value is 1, but dy is 0 and it is going to this direction. So, that means my x is changing, y is not changing by having the value 1. So, I directly put this 1 here, it is plus 2I, x is changing, but y is not changing. So, y is 1 and dy is 0 because there is no change in y here. So, I should put dx here. So, now I need to evaluate these things. So, what should be the value here? It seems to be minus of I y cube divided by 3 0 to 1, that is the first value, first integral value, plus this quantity, if I integrate, it will be x s cube by 3 minus x, and then I have plus 2 I x square by 2, the limit is 0 to 1. Fine. So, let us go back here. I need this, so I am not going to erase that. So, this quantity, if I put the limit, it will be minus of I 1 by 3. This quantity, if I put plus 1 by 3 minus 1 plus I. It seems to be something like this. Okay. So, let us check what value I am getting. So, before that I need to check once again everything is correct or not. In path 1 I am going to this way, this is my the value of z square is this x plus y whole square. So, x square minus y square and 2 x y, and dz is dx plus I dy, it is correct. Now, I am going to path 1. In path 1, if I go from here to here 0 0 to just 0 1. So, my x is not changing, x is 0. So, minus y square, and then this is 0. So, minus y square dx dy I dy. So, this is okay. So, this part is fine. So, let me first find out what is the value, then I will check things are correct or not. So, it seems to be I minus I by 3 minus 2 by 3. So, it is 2 by 3 I minus 2 by 3. So, it is 2 by 3 I minus 1. It comes to be something like 2 by 3 minus I with path 1. So, let me write down the value. I will do that for other path. So, let me write down the value here. So, for this path, the value of integration, I write it here, it is 2 by 3 I minus 1 for path 1. Okay, I will do the same thing for path 2 and so on. So, let me erase these things and put it somewhere here, so that it will be easier. So, my fz dz integration is comes out to be x square minus y square plus 2 I x y dx plus I dy. This is the integration, total integration I need to evaluate. So, path 1 I have already evaluated, it is 2 by 3 this. Now, what about the path 2? So, integration 2, which is path 2. So, in path 2, that means this path, what happened? Initially the change over x is there, but there is no change in y. So, that means y is 0 and x is changing. So, integration x square minus y is 0. So, I should not bother about y. This quantity is also be not be there, dy is not there. So, it will be just dx. This is the first part, the first segment of line is given like this, and the rest part is plus, the limit is 0 to 1 because x is changing from 0 to 1 here. What about the next path? Next path is integration, y is changing. So, limit 0 to y, the value of x is now 1. So, 1 minus y square plus 2 I, x is 1, y is changing. So, y dy is not changing, dx is not changing, dy is changing. So, it is I dy. If I evaluate the first part, it is x s cube divided by 3, 0 to 1, the first integration. The next part term by term. So, I take it outside. So, it is y minus y cube by 3 integration. This quantity is plus 2 I y square by 2 with the limit 0 to 1. The first term comes out to be 1 by 3 plus I, y is 1 minus 1 by 3 plus this 2 is cancelled out. So, plus I. This quantity, if I evaluate, it is 1 by 3 plus 2 by 3 I minus 1, which is equal to 2 by 3 I minus 1. 1 by 3 minus 1 gives you minus 2 by 3. So, minus 2 by 3. So, this quantity. So, path 2 also I am having the same value, 2 by 3 I minus 1. I evaluate the integration over path 1, I am getting this value. I am evaluating the integration for this path, I am getting this value. The last part is that. So, let me do that also. Okay. So, in the last path, if you see carefully, then you will find that it is coming from 0 to, it is going from 0 to 0 to 1 point, and the relationship between x and y is simply x is equal to y. So, there is a line over which x is equal to y is satisfied. I am going to that line only, where m is equal to 1, rather y equal to mx plus c. Here c is 0. So, y equal to mx, m is equal to 1 because it is going to 0 0 to 1 1. So, slope is 45 degrees. So, that the relationship between x and y is x equal to y. So, just I replace these things and then things will be easier. So, when I replace that, the first term will going to vanish because x is equal to y, this term will not be there. So, the integration is simplified as 2I x square, because y is now x, dx and these things. So, it will be dx plus I dx, x is changing from 0 to 1, it will be something like this. Now, it is 2I multiplied by 1 plus I, and then I integrate this 0 to 1 x square dx. If I take dx common, then it will be 1 plus I. So, 1 plus I and 2I I will take outside. The integration is over x squared 0 to 1. So, it will be something like this. So, it will be 2I 1 plus I, and x square 0 to 1, it will be x cube by 3 0 to 1. If I put that, it is 2. I now multiplied these 2 inside. So, it will be I minus 1, and if I put the limit, it will be 1 by 3. So, it will be 2 divided by 3, this quantity. Again I am having the same value. So, my final for this path I will also have 2 by 3 I minus 1. I will have this value 2 by 3 I minus 1. So, here one interesting thing, very interesting thing, after doing all this calculation, lengthy calculation, not very much lengthy, but very straightforward calculation, I find that when the function is given like this, when I integrate this quantity, the result, whatever the result I have, is path independent. It is path independent. That means, whatever the path I choose, at least for this particular form of the function, there is no such change. If all the values are merging to a same value, and it only depends on the final and initial value. So, that is why it is path independent. Whatever the path you like, you can go, but the end result is same. Now, why is that? The reason is that here I will again show one example that will be more easier to understand. The reason is z square here is an analytic function. So, z square, since this is an analytic function, this analytic function, integration of an analytic function over a path is not depends on the path at all. So, it depends only on the initial and final value. So, since z square is an analytic function, we have this property, but if I took a different function, then things may not be the same. So, let us try to do that also. I will take now okay, let me try with these things to another function. This is path 1. I am doing the same problem for another. So, let us do that. Fz is fz, okay, let me change the path. So, I am not going to do the entire 3 paths, but 2 different paths. So, zero 0 1 1, I am going to this path, 0 0 1 1, I am going to this path, just 2. where I am going to directly from here to here, and another I am going to this, just to check. This is only for checking. So, my function is z equal to z star, f z is equal to z star. So, we know that z star is not an analytic function. So, that is why if I try to find out the path integration, it is likely that the two values may not be the same. So, we try to do it quickly. So, that means it is x minus I y, and the integration over path 1 is x minus I y dx plus I dy. This is the integration I have. Okay. Let me simplify this integration, path 1. So, it is x dx plus y dy plus I integration of x dy minus y dx. This. Okay. So, I separate out and then I put. So, the first case, the first part is like the previous problem, the relationship between x and y is just x equal to y. So, here x equal to y is the relation. When I put this relation here, then I will readily find the integration if I put x equal to y. So, 2 of x dx, because y will be x, dx will be dy, and then if I put, it will be something like this, and my limit is 0 to 1. However, when I put x equal to y here and dx equal to dy here, this quantity seems to be vanished, because this minus this seems to be 0. So, I will have 0. So, here what value I am getting? 2 x square by 2, 0 to 1, which seems to be 1. Okay, one value I am getting which seems to be 1. Okay. So, I will have the integration, the value of these things is 1. What about the other path? For path 2, for path 2, what we are getting? For path 2, in the first part from here to here, I do not have any change in y, I just only change in x. So, and y is 0. So, this quantity is going to vanish. So, I will have x dx plus I, this quantity dy is 0 and y is 0. So, I will have something like 0 here. X is changing from 0 to 0, but dy is something which is not changing. So, that is why I put dy is 0. Here y is 0. So, I need to put it, and then. So, the limit is, this is the first part, the limit is 0 to 1. What about the second path? The second path, I mean second portion of this path, this is second portion of this path. So, what happened? So, x is now fixed to 1 value. So, dx is now 0, y is changing. So, integration of y dy with the limit 0 to 1 plus I, x is 1 and dy is changing. So, I should have this quantity, x is 1 and dy is changing, dy, but here dx is not changing. So, this quantity is not be there. So, this is the entire thing I have. So, here I have something x square by 2, 0 to 1, this is 0, plus y square by 2, 0 to 1, plus something here which is interesting, plus I y 0 to 1. Let me check once again. The first part y 0 0 1 1, there is no change in dy. So, dy is 0 and only the x is changing. So, that is why I have these things. Here dy is 0 and y is also 0. So, this quantity also should not have any contribution here. In the next part of these things, this portion have x dx. So, x is not changing. So, this will not be there. So, only we have y dy, these things, and for this part x is not changing, it is a fixed value, that is 1, and dy is changing. So, I should have this contribution, but here dx is not, dx is 0 because x is not changing. So, this contribution will not be there. So, I will have integration of I dy that I have. So, after doing all these things, I find that this is half plus half and this quantity is plus I. So, as a result, I will have something 1 plus I. So, that means if I go from here to here and if I go from here to here, both the cases I will have the integration, but this integration have quite different values. The reason behind that, as I mentioned, this is a very simple checking that whether the function is analytic or not. So, here my function f z, which was z star, was not an analytic function. Since this is not an analytic function, the integration is not depends, it depends on path. So, it is a path dependent integration. So, for this case we have a path dependent integration, and this path dependent integration is coming with the fact that if the function is analytic. So, today we will learn a very important thing. The first thing is that if the given function is analytic and if I want to integrate over some given contour, if the function is analytic, I should not bother about the contour, the line, rather the initial and final value is important, because the integration is entirely depend on initial and final value. If I go from one point to another point on any path I like, let me show that. From this point to this point, if I go with this or with this, since this point is fixed, integration of f z dz will be same for all the path. So, if it is path 1, if it is path 2, if it is path 3, then integration f z dz is equal to integration f dz is equal to for all the cases it is same. And with that we can have a very interesting thing that we will show in the next class, that if I go from this point, say point A to point B with this direction and return back to the opposite direction. So, what happened, path 1 is equal to minus of path 2, and if I add 2, then I have a closed path. So, A to B and B to A. So, I will have a closed path, and if I integrate that closed path, I will always have 0. So, that is a very important outcome, that is because I am going from this to this and from here to here. Since it is a path independent, if my initial and final point is same for analytic function, obviously here f z is analytic, I will always have this relationship, which is a very important relationship, and in the next class we will explore more about this relationship and try to find out more interesting thing regarding this relationship, which is generally called Cauchy-Gauchard theorem. This is one theorem which is called Cauchy-Gauchard theorem. We will go in the next class, we will try to understand in detail and try to prove that in a different way, that how these things is working and all, and how this can be useful to calculate some integration. So, with this note, let us conclude this class. So, in the next class we will start from here. The path integral is the important thing, is the most important thing in the complex analysis. So, we just started the path integral. So, we will continue this concept in the next few classes and try to understand using this the relationship, this beautiful relationship, the closed integral of an analytic function is 0, how we can evaluate different form of integration, and how do I know, I mean the different integral forms. So, with this let us conclude this class. Thank you for your attention. So, see you in the next class.